In this video, we're going to be looking at a new concept called the indefinite integral. So far in this course, we've been studying what's called differential calculus. So we have been studying how functions change and developed a way to quantify the rate of change, and that was all about the derivative. So we've been working with the derivative for the whole course so far. Now we're going to switch gears, and we are going to focus on what's called integral calculus. So we're going to go from differential calculus to integral calculus, and there's two big things that we're going to be working on with integral calculus. First of all, and that's what we're going to be working on in this video, is we are going to try to come up with the function if we know its derivative. So for instance, if we know the derivative is 3x squared, what was the original function that had this derivative? So what was f of x? This process is called finding the indefinite integral, or finding the antiderivative. So it's kind of like we're undoing the derivative. The second big concept in integral calculus is finding the area between curves, or an area of a region. Let's start with the power rule. So remember, when we were taking the derivative of a function where we had to use the power rule, let's say the derivative of x cubed, what we did was first we put the exponent down in front, and then we add x to the 1 less. So we subtracted 1 from the exponent. So we have 3x squared. Now if we're trying to undo that, we're trying to find the indefinite integral or the antiderivative, we have to do the opposite. So we have to add 1 to our exponent. So if we're trying to if we have 3x squared and we're trying to get back to this original thing, we have to add 1 to the exponent and divide by that new exponent. So this would give us 3x cubed divided by 3, which is just x cubed. So do you see how if we start with this, what I need to do is I add 1 and divide by that new exponent, and that will get me back to where I started from. One thing to notice is that you're doing the opposite thing. So we're adding 1 to the exponent instead of subtracting 1 from the exponent, and we're dividing instead of multiplying. But the other thing to notice is that we're doing it in the opposite order. So before, when we were doing the derivative, we multiplied by the power and we subtracted 1 from the power. This time we add 1 to the power first. That's the thing that we did second last time, and we divide by the new power. That's the thing that we did first when we were doing the derivative. So we're doing the opposite, and we're also going in the opposite order. Here's our power rule using mathematical notation. So just like we had notation for the derivative, like for instance we had dx of x to the n is n x to the n minus 1. That was our notation for the derivative. We're going to have notation for the antiderivative, or the indefinite integral. So we have two things that we need to see when they're telling us that we're doing the antiderivative or the indefinite integral. First, we have this integral sign, and then we also have this dx sign. These two together tell us that we're supposed to do the antiderivative. In order to do the antiderivative of a power, you raise that power by 1 and you divide by the new power. Now let's look at this plus c thing. What is that all about? So c is just a constant here. And the reason why we need that is because if we were taking the derivative of, say, x cubed plus 4, we would get 3x squared. And if we were taking the derivative of x cubed minus 21, we also get 3x squared. So if we have this constant that's being added here, so here the constant is 4 and here the constant is negative 21, we don't know when we're going backwards, when we're starting from the 3x squared and we're trying to get back to here, we don't know what this constant was. So what we do is we just say plus c, indicating c is any constant. For instance, if we were using the power rule on the following, So if we were supposed to find the antiderivative of x squared dx, I would raise my exponent by 1. I'm going to have x to the 2 plus 1, and I'm going to divide by that new exponent, that's 2 plus 1, and then I'm going to have plus c to indicate, okay, there might be some number that's added to this, and this takes care of any function whose derivative is x squared has to have this form, x squared, x to the 2 plus 1 over 2 plus 1, so we would end up with x cubed over 3 plus c. Before we move on, notice that once I've used my power rule to do the antiderivative, to find that indefinite integral, or to find the function whose derivative is x squared, the integral sign and this dx go away, because those are the things that tell us to do the antiderivative or do the indefinite integral. So those are now gone, and in place I have that antiderivative. I use the power rule, and I have that plus c. The last thing I want to talk about is how this power rule really only works for n does not equal -1. They have this restriction here. Well, why is that the case? Well, look what happens. If n equals -1, it means that I've got x to the -1 dx, and if I try to use the power rule, I would have x to the -1 plus 1 over -1 plus 1 plus c, and that would give me x to the 0 over 0 plus c. Now in math, we do not allow dividing by 0. That's illegal. So we cannot use this rule for when our original function was x to the -1. And we'll see on the next page what we do instead. So here are all of our rules put together. So we just saw this one here. This is x, the power rule, x to the n dx. We have x to the n plus 1 over n plus 1 plus c, and this only works for n does not equal 1. So an example of that might be the antiderivative of x to the 7th dx is going to be x to the 7 plus 1, that's x to the 8 over 8 plus c. Now, if we have just a number inside our integral, so maybe we're trying to find the integral of 2 dx. Remember, what we're trying to do here is we're trying to figure out, well, what function, when we take its derivative, gives us 2? So that would be 2x plus c. So when we take the derivative of 2x, we just get 2. So it can look a little funny sometimes, because when we have this, when we just have 1, maybe they write it like that, 1 dx, or maybe they just write it like this without the 1. If that's the case, the antiderivative is x plus c, because this is saying what function, when we take its derivative, gives us just 1 dx, and the answer here is x plus c. Now, if our exponent is -1, that means I have something like x to the -1 dx, or 1 over x dx. So if you remember, what function, when we took its derivative, gave us 1 over x? Well, it was the natural log. So the antiderivative of x to the -1 is the natural log of absolute value of x plus c. Moving on to the exponentials. So remember, when we took the derivative of e to the x, we just got e to the x. So the antiderivative of e to the x is just going to be e to the x also. Now here, if the base is different than e, remember when we were taking the derivative, so for instance, if we had d dx of 2 to the x, we ended up with 2 to the x times the natural log of 2. So if we were doing the opposite, if we're trying to find the antiderivative of 2 to the x dx, then we're going to get 2 to the x, but we have this natural log of 2 factor that we have to divide out. So if we have b to the x, we're going to have b to the x over that natural log of b plus c. And we have here in the derivative it's multiplied, so in the antiderivative it has to be divided. So let's work one quick and fairly easy example here. So if we're trying to find this integral, remember when we were doing the derivatives of something like this, we did the derivative of each term, term by term. And that's the case for the antiderivative also. So we're going to do the antiderivative term by term. So I'm going to write this out this time, but you don't necessarily need to do this. So we're just going to go term by term, taking the antiderivative. And also remember, when we had coefficients in front of our x, when we were using the power rule, or any rule actually, they just sort of went along for the ride. And so that's going to be the case when we're doing the antiderivative too. So the coefficients just kind of go along for the ride, and we take the antiderivative of the x part. So here we're going to have x to the 4 plus 1 divided by 4 plus 1 minus 7 x to the 2 plus 1 divided by 2 plus 1 plus 8 x to the 1 plus 1 divided by 1 plus 1 minus 76x plus c. Now notice I have done the antiderivative, so all those integral signs have gone away, and my dx's have also gone away, and in place I have the antiderivatives and a plus c. Let's simplify a bit here. So in this step I have added those 4 plus 1 over 4 plus 1. I've done that arithmetic. And here, notice I have one term where I can simplify. And if you can simplify a little bit, I want you to go ahead and do that. See how I have a factor of 2 here in both of these? So I can cancel that factor of 2. So I'm going to have 6 fifths x to the 5th minus 7 thirds x cubed plus 4x squared minus 76x plus c. Before we finish this video, one thing I want you to notice is that because these two operations, the integral and the derivative, are opposite, that means that we can check our work by taking the derivative of what we have here. And if we take the derivative, we're going to have 6 fifths times 5x to the 4th. These 5's will cancel, and we just have 6x to the 4th. We have 7 thirds times 3x squared. These 3's cancel, and I just end up with 7x squared. That's this second term. Here I have 8x. That's the third term. And here I have minus 76. That's the fourth term. So this thing here should match what's in your original integral. And if it does, then it checks.